I'm Professor Rad, and this is Precalc video 327, Simplifying Trig Expressions. So in this video, we're going to practice some trigonometric algebra, or even really kind of a trig arithmetic of sorts, where we start out with a complicated looking trig expression, and we try to simplify it down to something simpler, really. So there isn't necessarily a simplest form for a trig expression. There are multiple possible simplifications that we can go through. But for purposes of this video, what we're going to be looking for is an expression that only involves maybe one trig function or even just simplifies down to a number. So let's get started with this first example. So we have secant theta over tangent of theta. And as we go through this simplifying process, we're going to want to document the properties that we're using. So if you've been keeping track of the properties on that trigonometric identities and properties handout that we started at the beginning of this unit, you might want to have that out and ready for some reference. So the only identity I know of that links secant and tangent directly is going to be a Pythagorean identity. And Pythagorean identities are best applied when you have one or more of the trig functions being squared. So since neither of these is being squared in the current expression, a good rule is to just turn it into sine and cosine. So that might make things a little bit messy, but once things are in terms of sine and cosine, those are like our key trig functions that will help us simplify. So I know that secant is going to be the reciprocal of cosine. So let's change that one first. So we're going to get 1 over cosine theta, and that's going to remain over tan theta. And we're allowed to do that because that's the reciprocal identity. Now, as we go through this, we're going to want to try and do just one identity at a time to make sure we know deliberately which identity is being applied where and how. So now that we've got this, let's write tangent in terms of sine and cosine. So I'm going to keep that 1 over cosine up top. And then tangent is the same as sine over cosine. And that's because of a quotient identity. Okay, so now that everything is in terms of sine and cosine, we can turn this fraction bar into division and see if we can simplify. If anything, we'll cancel out. So this is going to be 1 over cosine of theta divided by sine theta over cosine theta. And that's just, division. Rewriting a fraction as division. But we can rewrite division of fractions as multiplication by the reciprocal. So this is 1 over cosine theta times cosine theta over sine theta. So that's just rewriting as multiplication by the reciprocal. And now that we've got this written out as multiplication, we can see that the cosines are going to cancel each other out. So our cosines cancel and we get 1 over sine. And that's just from multiplication. And then let's finish this up because 1 over sine is, we can apply a reciprocal identity and write that just as cosecant. So why don't we do that? We'll write that as cosecant of theta, and that is by a reciprocal identity. So there we go. We've simplified secant theta over tan theta into cosecant of theta. All right, we're going to do 2 more examples of simplifying trig functions, or trig expressions, sorry. If you wanted to pause the video at the start of each example and see if you can work through it, feel free to do that. But I'm going to work through them step by step, just like with this one. For our second example, we have cosine squared theta minus 1, and that's over cosine squared theta minus cosine. So for this one, the way that I'm going to start it is different. I'm not actually going to start out with a trig identity or trig property. Here's why. What I'm noticing up top is that I essentially have like x squared minus 1. So that's a difference of perfect squares. So that can factor. And then in the denominator, I have cosine squared and I have cosine. So I have a common factor of cosine in the denominator, so I can factor that out. So the first move that I'm going to make on this one is to factor the numerator and the denominator and see if it simplifies like a fraction would simplify normally. So the numerator is going to be cosine theta plus 1 times cosine theta minus 1. And the denominator, we can factor out a cosine of theta. And that's going to leave us with cosine theta minus 1. And that's just factoring. So now, as we look at this, we realize both the top and the bottom have a common factor of cosine theta minus 1. Now, I will point out, this is kind of lucky. And I knew to do this because I worked this out ahead of time. So very often when you are simplifying a trig expression, you may not know what to do first. So don't let that stop you. Try something, anything. So try something that, seems like a direction to go in, and maybe it will lead you to a good path. And maybe it'll lead you to a wall and you get stuck and you have to backtrack and retry. That happens a lot with these, and that's okay. Okay, so it is totally normal to take a lot of missteps before you happen to luck into the one that's going to help you out. So in this one, using factoring is the one that happened to help me out. So the cosine of theta minus 1 is going to cancel, and we end up with cosine of theta plus 1 over cosine of theta. And that's just simplifying a fraction. Canceling common factors. Now, on this one, because I have a sum in the numerator, I'm going to split this up into two fractions because I know cosine over cosine is going to give me 1. So I'm going to rewrite this as cosine theta over cosine theta plus 1 over cosine theta. And that's just addition. Right, so all we've done is we've rewritten the addition of this fraction. Now cosine over cosine is 1. And again, that's just simplifying that piece. And then as before, we now have a reciprocal here. So now we finally get to apply a trig property. We can rewrite this as secant. So this is going to be 1 plus secant theta. And this was a reciprocal identity. Now we didn't get just a trig function in the end, and we didn't get just a number, but this is about as simple as we could expect to get something like this, where we have a trig function plus 1. Okay, now I do want to point out a common place that you might try to start something like this would be to use a Pythagorean identity, because we have these cosine squares. The reason I would advise against a Pythagorean identity for the beginning of this one is because everything is already in terms of cosine. So if the numerator had had something like sine squared theta and the denominator had this cos squared minus cosine, then I would recommend using a Pythagorean identity to get everything in terms of cosine. But generally, if everything is already in terms of a single trig expression, you don't want to, mess that up. You want to see if you can manipulate that somehow. All right, so let's do one more example of simplifying a trig expression. All righty, for this last one, we have tangent of alpha plus 1 quantity squared minus secant squared alpha all over tangent squared alpha. So when we go to simplify this one, there are two things that I'm noticing. So like two different paths that I might try taking. It turns out that either of those two paths is going to work. So it doesn't matter which approach you take first here. because ultimately we're going to end up needing to do both of these things, and it doesn't matter the order we do them in. So when I look at this, what my trained eye is noticing is that I have secant squared and tangent everywhere else. So I'm going to want to turn secant squared into tangent at some point. I can do that using a Pythagorean identity. And because this is squared, Pythagorean identity is a good approach to take. The other thing I'm noticing on here is that I have a quantity squared. So I'm probably going to want to FOIL that out at some point, unless something is going to factor nicely. So what I'm actually going to do is I'm going to multiply this out first, and then I'm going to apply the Pythagorean identity. But like I said, you could do that in either order if you wanted to. In fact, if you wanted to, you could also recognize this as a difference of perfect squares. So you could have tan alpha plus 1 plus secant alpha, tan alpha plus 1 minus secant alpha. I wouldn't recommend that one because it gets rid of the secant squared, and then that's going to be harder to get things in terms of the same trig function. But that could be another approach you take. So it just depends on what your eye sees first and the path you choose to follow. So let's multiply this out. Be very careful. We cannot distribute exponents. So this is not tangent squared plus 1. Remember, when you have a binomial and you're squaring it, you have to multiply it out. So we're going to have tan alpha plus 1 times tan alpha plus 1. Okay, so remember that you have to FOIL this. So that's going to give us tan squared alpha plus 2 tan alpha plus 1. So when we multiply that out, so when we do all our distributing and combine like terms, this is what we're going to end up getting. And then we'll subtract secant squared alpha all over tan squared alpha. And this is just multiplying out or squaring the binomial. Next, here's where I'm going to apply my Pythagorean identity. So my Pythagorean identity says that if I take 1 and I add tangent squared to it, I end up with secant squared. So what's happened when I did that squaring of the binomial, I ended up with a tangent squared alpha plus 1. So that's going to be the same as secant squared theta. So I'm going to take those two components and rewrite them as secant squared alpha. I got to keep my plus 2 tan alpha and bring down my minus secant squared alpha. And this was a Pythagorean identity. Now I'll point out, if you didn't see that, that's totally fine. You could also replace secant squared theta here with 1 plus tangent squared alpha. I keep saying theta, I apologize. You could replace your secant squared alpha with 1 plus tangent squared alpha. And you would end up getting a similar sort of simplification process. So it would still work out if you were to do that. But what's nice is that I have secant squared alpha minus secant squared alpha. So they cancel each other out. And we end up with 2 tan alpha over tangent squared alpha. And that's just some simplifying. But now this is like having 2x over x squared. So this tangent can cancel with one of the tangents from below. And we're going to get 2 over tangent of alpha. So again, that's just simplifying. But we, once again, can use a reciprocal identity here because we have 2 over tangent, and the reciprocal of tangent is cotangent. So we can rewrite this as 2 times cotangent of alpha, and that is from a reciprocal identity. So we have this beautiful mess that involves tangent and secant, and it simplifies to just 2 cotangent of alpha. That's going to be it for this video. In our next video, we're going to see how this applies to what we'll be looking at moving forward. So basically, what we've done in these simplifying processes is we've established a new trigonometric identity. In fact, we did 3 of them in this video. So in the future, we're going to be asked to establish an identity, and that problem is literally the same thing as this problem. It's starting with one side and simplifying it until you get to the other side. So I'm looking forward to seeing you in our next video where we go to establish trig identities. I hope this helped you practice your trig identities a little bit more and become, more comfortable manipulating trigonometric expressions. So I hope you have a magnificent day, and I'll see you next time. Bye for now.